Imagine you have data so complex that to separate the red points from the blue points, you need to map them into a space with infinite dimensions. Calculating coordinates in infinite space is impossible. It would take forever, yet support vector machines do this every day, instantly. How do you calculate the impossible? Let's start in the visible world. You have input vectors, x and labels, y, either -1 or +1. You need a straight line to separate them, but look closer. There are infinite lines that could work. Which one is best? Vapnik's statistical learning theory gives us a geometric answer. The best line is the one that is most safe. We want the widest possible street between the classes. This is the maximum margin. We define our center line as W transpose times x plus b equals 0. Then we scale the equation so that the data points right on the edge of the street satisfy a strict condition. The absolute value of the function equals exactly 1. These specific points are the support vectors. They physically hold up the margin. Here's the geometry. The width of this margin is exactly 2 divided by the norm of W. To maximize the margin, we must minimize the norm. Mathematically, we minimize the squared norm of W. This is a convex quadratic optimization problem. That sounds technical, but it implies something powerful. There are no local minima. If you find a solution, it is guaranteed to be the global best solution. That works for straight lines, but real data is messy. In a dataset like this ring, where red points are trapped inside blue points, no straight line can separate them. We are stuck, unless we leave the 2D world. If we map this data into a higher dimensional feature space using a mapping function phi, the data becomes linearly separable. But this mapping comes with a terrible cost. To map just a two-dimensional point into a richer feature space, we might need to calculate terms for x squared, y squared, x times e, and so on. As dimensions grow, the number of calculations explodes combinatorially. For high-dimensional data, calculating this mapping explicitly is computationally lethal. This is where the kernel trick saves us. It turns out, to find the optimal boundary, the algorithm doesn't need to know the coordinates of the points in that high-dimensional space. It only needs to know the dot product between them. A kernel is a function that computes this dot product directly from the original inputs. Let's prove it with numbers. Take two 2D points. If we use the polynomial kernel, 1 plus x transpose z quantity squared, we are doing a simple calculation in 2D. But if you expand the algebra, it equals exactly the dot product of two vectors in 6-dimensional space. We implicitly mapped to a space with coordinates like √2 times x1 without ever actually writing them down. It gets wilder with the Gaussian or RBF kernel. The formula is just an exponential based on distance, but if you expand this exponential, you get an infinite series of terms. This means the Gaussian kernel behaves like a dot product in infinite dimensional space. Thanks to Cover's theorem, in this infinite space, your data becomes arbitrarily separable. We can classify anything. But in the real world, data is noisy. If we force a perfect separation in high dimensions, we fit to outliers and ruin the model. We need to relax. We introduce slack variables, Greek letter xi, which allow points to violate the margin. We update our goal. Minimize the norm of W plus a penalty C times the sum of these violations. The parameter c is your control knob. A large C imposes a huge penalty for errors, forcing a strict, narrow margin to classify training data perfectly. A small c is more forgiving. It allows a wider margin and some errors, which often generalizes better. This is equivalent to minimizing the hinge loss, which is 0 if you're right, and linear if you're wrong. To solve this efficiently, we don't solve for W directly. We use Lagrange multipliers to flip this into the dual problem, solving for variables lambda. Here's the magic. The dual formulation depends only on the kernel values between points. It never touches the raw dimensions. Furthermore, the solution is sparse. For most points, lambda is 0. The only points that matter are the support vectors. SVMs aren't just heuristics, they are statistically consistent. As you add more data, the SVM decision boundary converges to the optimal Bayes rule, the theoretical limit of predictive accuracy. In regularization theory, the SVM is minimizing empirical risk, how well it fits data, plus a regularization term in a reproducing kernel Hilbert space. The theory holds up in practice. In text classification on the Reuters dataset with nearly 10,000 dimensions, SVMs achieved 87% accuracy, beating naive Bayes at 72%. On the USPS handwritten digit dataset using a polynomial kernel, SVMs achieved a 3.2% error rate. For context, the human error rate on that task is 2.5%. Support vector machines represent a unique moment in machine learning history. They combine the geometric intuition of margins, the optimization guarantees of convexity, and the infinite reach of kernels. They don't just find a solution, they find the optimal one.